Okay, so chapter 4. So, can someone talk a bit about what you did in chapter 3 so that we have a setting for chapter 4? And by someone, I'm referring to the three of you who just read like basic chapter 3 stuff. It's okay if it's a
Okay,
bad overview. Ajay, I see you unmuted yourself. Sorry. Yeah, go ahead.
okay. So like the broader overview of that particular was like uh, how we should evaluate like our model so that we know like it would perform better on the data that it has never seen regarding it, and like the general trends of like the different overfitting, or like how we are doing like that bit. Yeah, broader overview I can say.
Okay, so overview of generalizing to unseen data.
Yeah, yeah.
Okay, what was the title of the chapter? I forget. 3 point model evaluation. Okay, so you're evaluating model, seeing what is overfitting under what situations overfitting is happening, minimizing errors, in sample out of sample errors, empirical MSE, cross validation. Oh, okay, so this was oh, by the way, I all of this came up in my Microsoft interview, so I want to thank everyone. More on that later. So, chapter 4 is basically having spent enough time running down linear regression and thought about evaluating predictive models. We are trying to now figure out alternatives to linear regression based on smoothing. And recall that smoothing was this general idea that at a high level, there is some structure in the data. That is the assumption we are working with. If that assumption is false, then there is no structure and you can never learn anything. So again, the question is what is the best you can do? Assume there is some structure in the data, try to learn that structure. um, and by smoothing, he says that the smoothing is basically a weighted average of the observed responses. So predictions are the y's, observations are the x's, and the estimator of those y's, which is called mu hat of x. And recall that mu of x is typically what we take the estimator as. The terminology for it is mu of x because it is a function of the observations that is used to predict a response. Um, but here it is slightly different, right? The predictions are going to be weighted averages of the observed responses in the training data. So xi yi is your training data, and you use your xi and yi with a particular weight function w to create an estimate of your prediction at a new point x. So that is exactly what this formula is telling you. Prediction at a new point x is a function of past data. Okay. Um, Most smoothing methods have a control setting written h that says how much to smooth. So smoothing can be done in different ways. You can take just a simple average of all of your data, and that is a smoothing in a sense. So you're drawing a mean, the mean line that you've seen and your data is scattered around it. That sort of plot you can imagine. Um, that is one form of smoothing. There are other forms of piecewise smoothing, where piecewise basically means you take small sets of data, smooth it, small sets of data, smooth it, small sets of data, smooth it, and then connect those things. So in the similar spirit, H basically determines how much to smooth. So he gives an example with k nearest neighbors. The weights are 1 by k if xi is one of the k nearest points to x and w is equal to 0 otherwise. So you don't consider other points, but you consider points close to it within a certain limit, and that's your k nearest neighbors. So with kernel regression, which is another technique that we're looking at now, where the degree of smoothing is controlled by this bandwidth h. Um, And now what we are looking at is for a particular method, kernel regression, how much should we smooth and how to pick the right amount of smoothing. Obviously, less smoothing leads to less bias. You can think of, I should move this away. Less smoothing leads to less bias. If you have this is what your data looks like. Sorry, I should draw it bigger. So if you smooth it like that, and then like that, and then like that, and like that, your bias, which is the perpendicular distance. So this will be when you finally draw your line. This will be your bias, different distance from the points to the line, right? And he's saying that this bias will obviously be lower for the lower number of points you take in smoothing. Why is that the case? If you imagine, if you take all the points and draw a line through it, then you'll probably end up with something like that. And you can intuitively think of it like this distance is much greater than its distance to the pink line for each point. And I don't know if that's strictly true. I'm trying to think of a case where it isn't true. But yeah, just to get at what he's trying to say, less smoothing leads to less bias. More smoothing leads to more bias. However, smoothing less increases the variance of our estimate. You can see that this line is varying a lot more than the black line, right? So I'm going to use that as an example, but I don't know if that example is valid or not in this for this statement. I think it is because I can't think of a corner case, but that might just be because I'm not thinking enough. Anyway, I've seen this before. If you haven't, please stop me because this was a crucial part of the first couple of chapters. Total error is equal to noise plus bias squared plus variance. Now the noise we can't control, so we ignore this and we look at this bias variance, and then we think about what can we reduce, what can we change, etc. So this plot basically shows that bias goes up as variance goes down, and noise is roughly constant for slightly increasing, but roughly the same for um, different levels of smoothing. And as a result of which, you can think of the generalization error as a sum of bias and variance, um, which is this black line. So that's the decomposition of the generalization error in terms of the bias, the variance, and the fixed noise. We say fixed noise in the sense we can't change that noise. It doesn't mean that that noise is a fixed constant value. So chapter goes on to talk about what is this, adapting to unknown roughness. I see. So we talked about Taylor expansions here, and this is important. You should definitely look at this. You should read about Taylor expansions. Kumbhojkar had Taylor expansions for the record, so you've all studied it for a fact. I know that for a fact. It's just that you need to think about what it actually means now, rather than just looking at example sums and solving them. So Taylor expansion at a point basically tells us about the value of a function around that point, and that is done by using this particular partial uh, derivative and expanding it about that point. Look up the equation. I'm not going to get into details here. But yeah, Taylor expansion. What were we talking about again? We are saying uh, take a graph of two functions r and s. Both are smooth functions in the mathematical sense. We could Taylor expand both functions to approximate their values anywhere, just from knowing enough derivatives at one point. If instead of knowing the derivatives at x0, we could have the values of the functions at a sequence of points, we could use interpolation to fill out the rest of the curve. This is true. Quantitatively, however, R is less smooth than S. It changes much more rapidly with many reversals of direction. For the same degree of accuracy in the interpolation, R needs more and closely spaced training points xi than does S, and this diagram shows what all of this means. So we're saying R is a less smooth function than S. So the green is the true R and the green is the true S. The orange, or what I'm drawing here, are the points that we get. And let's say that you get equally spaced samples for both of them. This, this, and this. Now, in order to reconstruct S, we will make some smoothness assumption and reconstruct. But what he's saying is the same smoothness assumptions doesn't work for R, because R is much less smooth, or much more, less smooth means more variance. Now you see clearly what that means. It changes much more rapidly with many reversals of direction. So that's how this works. Um, and now he gets to saying that suppose we don't actually get to see R and S, but rather just R of x plus epsilon and S of x plus eta. So eta and epsilon are noise and x is some random point. Um, so you get to see the function of the value of function R at this x and the value of function S at this x, and these are called like noisy samples because clearly there is noise added to these samples. I'll assume that these noises are a constant variance IID Gaussian noises with sigma equal to 0.15. Okay. Just again making assumptions about the noise to make our life easier. As remarked earlier in chapter 1, if we had many measurements at the same x, then we could just find the expectation at averaging and find the exact value of the function. And this would convert. I assume you have been through this, but this is like an important takeaway from chapter 1. So if you haven't been through this in detail, then please, like, if this seems unclear, then please ask, and like go back to chapter 1 first, read that, and then ask. So the idea is the optimal predictor is the conditional mean. I hope that that is like a not too confusing statement. The optimal predictor mu of x is the conditional mean of y, the response variable, given x is equal to x. And I learned this last year, so I don't blame you if you don't understand. I'm just saying go back and read. Anyway, the point of this is that there will always be a mean squared error, the noise variance. However, our estimate would be unbiased. What is an unbiased estimate? One whose expectation converges to the true value. So, I feel like we've been over unbiased estimates, so I'm not going to go over it again. Never mind. Plus, this was supposed to be a half an hour summary. Yeah, smoothing methods try to use multiple measurements at point xi which are near the point of interest x. So now, okay, let's step back and go to a high level overview. He said that if you want to estimate y given a certain x, right? This is your y, this is your x. Y and x are random variables. They take certain values. And he's saying that if you had now assume the setup where you have noisy samples, and assume that if you have multiple y's at every x, then you can basically take the expected value and you can average out the noise, because noise is zero mean. Remember, expectation of noise is zero, and by linearity of expectation, which is expected value of mu of, no, I'm not going to use mu, we used R and S, right? Expected value of R of S. Holy shit, this is harder than it looks. R of X plus epsilon. This turns into an expectation of this plus an expectation of this. Sorry for the bad writing, but hopefully you get it. This is called linearity of expectation, and we know that this expectation goes to 0 because noise is zero mean, and therefore this is an unbiased estimator. This converges to the true R. Yeah, the notation is really bad, but hopefully you understand what I'm trying to say. So the point being, if you have 3 observations, then you can average out the noise. But the fact is, forget 3 for each x. We don't even have 1 for each x. So you You don't get 1 1 1 1 1 1. You can't like directly draw the function. You get like estimate here, then you'll get here, you might get one here, and now suddenly you're supposed to interpolate between these, which means draw between these points without actually knowing all of these intermediate values. And that is where your smoothness assumption comes in. So he's saying that in that case, I forgot what he was saying, but this is the setup that he was describing in these last two paragraphs. Anyway, he's saying, oh yeah, he's saying in that case we can do a Taylor expansion about these points, or we can use the estimates close to these points. If you don't actually have this point, then you use these estimates close to it to make an approximate prediction at this point. And that is the idea of where the Taylor expansion comes in. You can derive the form for it and then make a prediction at this by substituting the values of its closest points. Um, and like we discussed before, there is some sort of weighting scheme W we use over these points in order to arrive at this estimate for this particular point. Let's call that x, small x. I will pause. Any questions so far about this high level understanding? There should be many.
I have one doubt.
Yeah.
So, you said that by using Taylor expansion, we will find the points near the point we want to predict, and then we will assume a function, right? So, if we don't know if we don't have the data point, then how will we find the neighboring points? And like,
Right.
for example, in your diagram,
Mm-hmm.
so the point which you have marked with an arrow,
Mm-hmm.
we don't actually have that point, right?
That is true.
Yeah. So what he said that we will get the neighboring points using Taylor expansion.
We will not. So okay, maybe I conveyed it wrong. We will not get the neighboring points. The setup here is we want to make a prediction at a point x, and we have some points xi and xj which are close to it but not the same point, and we want to use xi and xj to make a prediction about x. And then there will be some averaging scheme using w, the weights, over xi and xj, to make a prediction at that particular point x, or at least that's what I think he's trying to convey. Let me go back and read what he's saying. We have at the most one measurement per value of x, so simple averaging won't work. Even if we just confine ourselves to the xi where we have observations, the mean squared error will always be sigma squared, the noise variance. However, our estimate would be unbiased. Smoothing methods try to use multiple measurements at points xi which are near the point of interest x. If the regression function is smooth, mu of xi will be close to mu of x. Yeah. So he's saying that if this function is sufficiently smooth, then it won't be unreasonable like this. You see what I'm saying? And if it's not like this crazy function and it is reasonably smooth and these xi's are roughly close to x, then you can use the prediction of y, which is, and note that this is the prediction at xi, which is mu of xi. Yeah, mu of xi is the prediction at xi, right? I think so. Right, so again, to go over the whole setup again, we want to make a prediction at a point x. We do not know what prediction to make at x. We know the values of the prediction at xi and xj close to x. We use an averaging over xi and xj to predict the value at x. This much clear?
Yes.
Now, why does this work? This works because we make the assumption, the additional assumption of smoothness. What does smoothness mean? Smoothness means the function is likely to be smooth, or let's say flat, at points that are very close together, as opposed to very crazily varying at points that are close together. That is your smoothness assumption, and that means you can use Taylor expansion about this point x to make a prediction for it. Or is Taylor expansion entirely separate from it? Where was Taylor expansion measured? Let's assume that we can do a first order Taylor expansion. Yeah, Taylor expansion is basically using the distance from that x side to that x. Yeah, you see this? Taylor expansion uses the distance to the closest points to make a sort of prediction on x. That's the basic idea. At least that's what I seem to understand from this. But please ask me again if I'm not clear and I haven't answered your question.
Yeah. I got it now.
Okay. Other questions? Things I went over before that were unclear? You can ask. You don't have to be like guilty. I'm fairly sure Ananya feels guilty that she didn't study, so she's not going to ask questions.
It's like I have the notes by my side and going back and trying to figure out what my question was here.
Okay. Whenever you come up with it, let me know. Okay. Seeing no questions, please go through these things. These are very important, and get back to me if my notes are unclear, or if you want additional explanation, post on the group. I will be slow to respond, but I will respond. Okay, so we went through this stuff. Basically, you are expanding this into the noise, bias, variance, decomposition. And then you're saying you're trying to analyze how those values change with increasing data. In general, variance shrinks when you get more data, mainly because you start seeing more of your population. And like, again, this goes back to the underlying assumption of smoothness. If a function is smooth, then the more data you see, the more structure you will see. The more structure you see, the less the variance. That's it. At least that's how I think of it. Anyway, variance shrinks as you get more data. And this analyzes all of the rest of the terms in this equation, which you should definitely go through. And to give you a high level overview, like when you work through these things, write down stuff like this. Like, I still write these down because I tend to forget what was mu hat, what was yi, what was wi. So like, if you have to write down the names of these things, and if you want to change them to new variables, so that when you write these equations down, you have to force yourself to think back, and then rewrite it. That's one good way of ensuring you understand this. Whew. Okay. This was a part we spent a lot of time on. We had a lot of questions about. And I honestly don't remember what the answers were, but I do remember we sort of solved it. And Fennel pointed out that there was something in TALR that was relevant to this, so I would strongly suggest you read about that first. Let me just go through this to sort of, okay, to illustrate. Let's just, no, that's not it. The same figure size creates a much larger bias with the roughly more rapidly changing R than the smoother, more slowly changing S. Varying the size of the averaging window will change the amount of error, and it will change it in different ways for the two functions. So the averaging window is we defined a weighting scheme that we said was used for averaging. This is talking about that weighting scheme. If that changes, it will change the amount of error, and it will change in different ways for the two functions that are the smoothness of which is different. So that's what this is saying. And then he steps into a more careful second order Taylor expansion. Order is basically the squared terms, so order of the polynomial, recall that. In this case, first order relies on order of the derivatives. So, no, not the derivatives, still the coefficients, but second order terms will involve second order derivatives. And this is the form of kernel regression that we got from Wikipedia. So you will want to look up kernel regression on Wikipedia. I think Fennel had sent that. And each of these terms, you can expand this out. We did expand this out. As you can see, it's written down here. It's also there was a discussion of why this is 0, what this is exactly. So let's actually step back, and I can at least tell you a high level idea of what this term is, right? I can pause here, like if any of the people, like you know that mu hat is an estimate at x, you know that mu is the true value of x. So can someone tell me what this term is? I will give you a hint. There is a sentence that describes what that term is right before.
Oh, it's the bias, right?
So
Go.
the bias at x is basically the expected value of an estimate minus the true value. So that is your bias. In general, recall that I'm not going to go back into what bias is. You guys should know what bias and variance is by now. Screw it, I will tell you anyway. This is your true function. This is the function you learn. You take the means of both of them. Difference between the means is the bias. Again, think back, expected value is the mean. You're taking the expected value of two quantities by the linearity. This will be expected value of one minus expected value of the other, which is this mean minus this mean, which is this. This is your bias. And that is what you're taking given your data. Why given the data? Because the data changes constantly. When the data changes, the predictions will change, the bias will change. So conditioned on the data, this is the bias. Okay, where F is the density, sigma square is the variance of the, honestly I don't know what this is. I will know if I read this, but I'm not reading it, so it's okay if you don't understand it either. Just know that this is a very important section that you should definitely spend time on. The general idea that they are trying to convey is that this bias and variance can be decomposed, and it is proportional to h square in this case. H again was the scheme that we used, the averaging window. It's also called the bandwidth at a later point for kernel regression. And every time, so why do all of this detailed analysis? Because you want to talk about asymptotics. So in chapter 6 we see there's this very important statement that the reason statistics works is because first on one side you make assumptions that there is some structure, on the other side you make assumptions on your distributions and you make nice properties. You make the properties match your assumptions and magically you have statistics working in the middle. But that is what Chalizi says, that at both sides you're pushing things in with assumptions. You're saying हाँ कुछ तो true structure होगा process में. You are saying हाँ ये estimator की ये property है और ये asymptotically unbiased है और ये है वो है. So you force these two things to match and you have statistics, but naturally this doesn't necessarily arise. So this book focuses a lot on pushing those things a little farther apart and analyzing, okay, what happens. And that means you need to see how these estimators are dependent on all of its parameters, on all of its variables. And that's why all of these analyses are done. And for you guys, what is important is to understand how the math is derived, not how it works. That is fine. You will get that anyway in your courses. Right now, just understand how it is derived. If you understand that, you will start seeing how it works. Maybe I meant to say the other way around. You don't need to understand how it is derived. You need to understand how it works. My bad. Yeah, I would say don't stress yourself out if you don't get derivations. That you can always ask us, but at least try to understand how it works on your own. Then we can help you with the derivations, and then hopefully that both of those combined give you a better understanding. I'm sorry. Again, you just ultimately you observe this: the mean squared error, fixed noise term, some sort of bias squared term, some sort of variance term, and all of this is now expressed in terms of h, powers of h, and you will see why this matters once we start looking closer at it. So this equation basically tells us that there is a single optimal choice of bandwidth h, which is an optimal degree of smoothing, and we could find it by taking this equation, differentiating it with respect to the bandwidth, and setting everything to 0. So typically how you find the maximum value or the value of h that maximizes this function, it will be take a derivative set to 0 and solve for h. Typically how you do solve for your polynomials. And they do that, set it to 0 and solve for h. And again, we have clearly skipped over this, so you don't need to know what it means, but you need to understand that h is proportional to n raised to minus 1 by 5. So what this tells you is the optimal choice for your bandwidth, and bandwidth was your averaging scheme, involves the unknown derivatives of the function of the prediction at x, second derivative of the prediction function at x, plus the unknown density f of x and its unknown derivative f dash of x. So what is the point of telling us all of these things are unknown? It's basically conveying a paradox, right? That we started with the assumption that we don't know this density. We assumed some smoothness. We used points to predict. Then we said, okay, if we do some sort of Taylor expansion, we can predict at this point. Then we analyze the error of those predictions and we say that this decomposes proportional to the choice of your averaging. Then we say the choice of the averaging depends on the distribution of the data. So leading us back to, okay, but we don't really know the distribution of the data. So like what did we get? And that is what he's trying to convey. Was this part at least crystal clear to everyone? If it wasn't, tell me, because this should be.
Yes. So, what you are trying to say is like we know a relation between h and n, but it includes various unknown things. So ultimately, we don't know how to find the bandwidth, right?
How to find the optimal bandwidth.
Optimal bandwidth, yeah.
Yeah. Ananya?
I got this part, yeah.
Okay, so we seem to have come in a vicious circle. Now, what he steps back and says is one way of expressing this is to talk about how well a smoothing procedure would work if an oracle is someone who knows the truth. This is from the, typically in statistics you use the oracle in cases where if someone were to tell you the true exact value, then what could you do? And we'll see how this is helpful. If they were to tell us, then we could find an optimal bandwidth. But since we do not have access to these oracles, we need to estimate this optimal bandwidth. Once we have this estimate, then we get our weights and our predictions. And so a certain mean squared error. This is not the optimal one. This is just an estimate. So I start with some number and then find the rest. That's the idea. Now then, In this case, the mean squared error, this decomposition that we saw, which was some complex function in H in terms of the derivatives, the PDF derivative, and so on, this complex function will be the same plus a particular bias, because now our estimator might be biased. What would be really nice would be an adaptive procedure, one where our actual mean squared error using this estimate approaches the oracle's mean squared error, which it gets from the optimal value. This would mean that we are figuring out how rough the underlying regression function is, and so we are adapting to it rather than having to be told. So that's and he will highlight how this happens, but that is the idea, that okay, if we start with a particular value and eventually arrive at an unbiased estimate where the actual mean squared error approaches the oracle's mean squared error. Cool.
Swapnil, but this is just like a hypothesis kind of thing, no? But like we won't be like really getting that particular value because we don't know like what kind of data we would be getting like that way sort of.
This is correct, but this adaptive procedure can exist, and this rest of this shows you how.
Okay. But like if let's say we don't know like if what data would come like next time in future as such, so how can we adapt like as in like because we don't really know no, like data might like there might be cases of outliers too, like basically what I mean to say.
No, this
So this adaptive procedure, I'm not sure like how is it. I'm not able to like really kind of relate मतलब, how we would be able to adapt like kind of.
this is a great question. So again, I will point you back to when we started out. We said that if there was no structure, then we really can't do any learning. So we have to start with the assumption of some structure in the data. Now, once we start with
Okay.
the assumption of some structure, then you can start saying, okay, now how do I learn the structure? And that means that whenever your new data comes in, it will follow some original distribution, which we
Okay.
call the sampling or the true data or the data generating process or whatever.
Okay. Like yeah, basically we need to basically make a general like assumption and based on that assumption it's like that. But in like real life situations this might not be the case.
Even in real life, there is going to be some constant source of data, right? There will be some structure in the data. At least we
Yeah, yeah,
operate
that's
with that assumption. Human behavior has a pattern. Data is generated by human behavior. Nature has a pattern, and
yeah.
so on.
Okay.
So, yeah, I mean, it is a fair question. What if the data has no structure? Well, then you can't do any learning. Okay, great discussion. So, the most straightforward way to pick a bandwidth and one which generally manages to be adaptive is in fact cross validation. And k-fold is better than leave one out, but leave one out works. The usual procedure is to come up with an initial grid of candidate bandwidths and then use cross validation to estimate how well each of them would generalize. I mean, it seems fairly straightforward. Come up with a set of bandwidths based on what you know about the data. If I know that if I if, so again now coming up with this is sort of using prior knowledge. So you would have to know something about the data source in order to estimate, okay, these are candidates, like this set of values seems reasonable, this set of values seems unreasonable. Then once you have those candidates, you can start comparing each of them and pick the best one. And that is generally, that is how cross validation could be used. This is fine, not really that important. You can understand this on your own. So he points out, for reasons which we will drop out of the math, it's often reasonable to start with 1.06 into standard deviation of your data divided by n raised to 1 by 5, where Sx is the sample standard deviation of x, and n raised to 1 by 5 might have something to do with the fact that we saw h was proportional to n raised to 1 by n raised to 1 by 5. So these are all things that people say we empirically verified, which means we don't have the theory to support this, but we found that this happens. Not necessarily we don't have the theory, but at least that in practice we found this works. And in machine learning, you will come across a lot of this. Even the way research sometimes works is you find something and then you say, oh, but now how can I theoretically back this? And you come up with a theory to support it. Okay. Convergence of kernel smoothing and bandwidth scaling. Do I want to get into this? It seems like not that difficult. Yeah, I want you to go through this partly because I want, like, this section is basically about convergence. So what they're saying is, see how fast this mean squared error converges or goes to zero for a change in h. So this increases with h but also decreases with h. So is there a particular value you can choose such that this will decrease and this is the only term that will remain? And then he sort of, it's not hard math, it's just like trying to understand at what rate will you increase h such that the mean squared error goes to zero. When I say zero, mean squared error goes to this value so that the sum is zero. Remember that this fixed noise we will not be able to change because it is independent of h or n. Which is why people say that if you're fitting your data extremely well, then you're probably doing something wrong because you're in essence also fitting noise, and noise is not dependent on your data. Noise is independent. So how come you are able to fit it? Yeah, I will leave that section for you. Is there a harder section? Kernel regression with multiple inputs. Seems like the similar setup. But maybe I went a bit fast, so this is interpreting smoothers, average predictive comparisons. Feel like this will be a bit much. And that's, I think, the end of the chapter. Yeah, that's the end of the chapter. Maybe let's at least step into interpreting smoothers. I don't know if I will. So it's fairly straightforward. So what I was talking about was we've seen kernel smoothing in one dimension. This is right after the convergence end, and this idea extends that to multiple dimensions. I mean, you've been treating x as a scalar, but now you can just make x a vector, and then you can come up with a kernel. And here you will have to read about what exactly a kernel is. A kernel is a function that maps a set of values to a particular real value. That's the general idea. Any probability density function would work so long as it had mean zero and finite strictly positive variance. This is a kernel function. The same conditions carry over. Any distribution over vectors can be used as a multivariate kernel, provided it has mean zero and variance matrix is finite and positive definite. Okay, let's step into this. So when you translate from kernel regression on one, let's actually read the summary. So suppose x and y are one dimensional and the true regression function is continuous and has first and second derivatives. Remember that we need to make this assumption in order to actually find h optimal, which involves the first and second derivatives of the regression function mu x. Suppose that the noise is uncorrelated between different observations. Again, remember why we need to make this assumption, so that that sigma square is not dependent on any of these observations. So noise is uncorrelated and Gaussian, therefore independent. Then the bias of kernel smoothing is when the kernel has bandwidth h. Then the bias of kernel smoothing when the kernel has bandwidth h is along the order of h square, and the variance after n samples is of the order of 1 by nh raised to minus 1. That seems odd. So it was nh raised to minus 1. Anyway, the optimal bandwidth is of the order n raised to minus 1 by 5, which you will see in this convergence section. And the excess mean squared error using this bandwidth is order of n raised to minus 4 by 5. If the bandwidth is selected by cross validation, the excess risk is still this. This last sentence you will have to work a little to find out. I won't explain it because it honestly, I don't even understand it without reading the section before that. But why is this, again, why are we doing all of this analysis? The point was we want to see asymptotically what happens. Asymptotically means as you get a lot of data, what happens to this estimate. And we saw that in order for these conditions to hold and in order to arrive at the optimal bandwidth, this is what you have to keep it proportional to. So optimal bandwidth has to be of the order of samples, number of samples raised to 1 by 5, minus 1 by 5. Mean squared error will be of the order of number of samples raised to minus 4 by 5. And in your head, it should be going on which one is larger, which one is smaller. If it has negative coefficients, then that means it's in the denominator. Larger will result, whatever. So go on and think of all those things when you're doing that. And that is your summary in 1D. Now, when you want to extend this to multiple dimensions, we treated h as the bandwidth, but now in multiple dimensions, you have to have h in multiple dimensions. So instead of that, we just use the kernel. So your W, remember this used to be a W of xi, your x, W was a function of the closest points, the point at which you want to make the prediction, and h, your weighting scheme. But now in multiple dimensions, this W is replaced by this whole thing. So what are the properties of this thing to hold? We said that W was between 0 and 1. So it has mean 0 and finite strictly positive variance. You should read up on this condition actually. Why do we need finite variance? Why is this a condition? Because this will come up a lot. So go to Wikipedia or just Google it. You will have, because it comes up a lot, it's very easy to find. I don't know the answer honestly, but I know that it comes up a lot and there was a reason and I had read it. I think it's because you don't want it to take very large and very small values simultaneously, something like that. Again, some sort of smoothness assumption maybe. Anyway, the kernel functions for scalars had this property. The kernel functions for vectors obviously carry over the same properties. In addition, the variance matrix is finite and positive definite. So positive definiteness, I feel like this came up, positive definiteness, but read about it. What is positive definite? What is semi-positive definite? Where does this come up? Yeah, that's about it. And then it says if you're taking a kernel function, right, can we decompose this kernel function such that we can pick an optimal bandwidth for each kernel? Kernel here refers to a kernel for each component. So you're saying x, if I say x has a three-dimensional kernel, then can I pick h1 in this direction, x1, x2, x3. So can I pick h1 in this direction, h2 in this direction, h3 in this direction? Sorry, this should have been h2, not h2. Anyway, the point is it is actually possible to do this. So you can just decompose your vector kernel regression as a kernel regression in each independent dimension. Pick this. Oh, I could have used this. Yeah. Pick a bandwidth for each kernel, which in general should not be equal. And then instead of having a one-dimensional error curve, of course, we will have a d-dimensional error surface, but we can still use cross-validation. Hold on, give me a second. I will be back in a minute. Sorry about that. Okay, so multi-dimensional kernel, multi-dimensional losses, and we find that kernel regression will recover almost any regression function, interestingly. This is true even when the regression involves a lot of interactions among the input variables in complicated forms that would be very hard to express in linear regression. So if anyone ever asks you, but what would you do if linear regression has a interaction terms? Because typically in linear regression you assume your columns of x are uncorrelated, and that's also why you do PCA and you reduce dimensionality so that your correlated data is removed and you have independent uncorrelated data. Um, so that's the where you use linear regression, where you use kernel regression. And at that point I didn't find these plots, and these guys interestingly pointed out to me that I basically missed, there are 10 pages after the chapter that have all the plots. But before we end for today, and I'm already 15 minutes over, I do want to go through interpreting smoothers. It is the idea for a coefficient in a linear regression is very simple. If you say y is equal to beta x, or beta 1 x1 plus beta 2 x2 plus whatever plus noise, then what you're saying is if x changes by 1 unit plus 1, then y will change by beta times that 1 unit. So y will change by beta 1 times, and everything else remaining the same. So that is a simple interpretation of the coefficients. They're also the derivatives of the expected response with respect to the input. So del y by del x1 is equal to beta 1. So these are like very easy to sort of picture, but as soon as we introduce interactions, all of this becomes harder, even for parametric regression. And recall that, okay, so what is this parametric term that they use here? Parameters are what we call the betas, right? In linear regression, beta is your parameter, which means you will have a parameter for every input value and then you will interpret those parameters. Kernel regression is non-parametric, which means regardless of the x's, your h will be like the same for that kernel regression, or your h1, h2 in each dimension is independent of the data, so to speak. Not, I don't know how to technically phrase that, but I think that's what you imply when you say parametric versus non-parametric regression. Anyway, think about that, tell me if I'm wrong. A reasonable way to produce a curve for each input variable here. So now what happens with. I'm trying to get at the point of this before actually explaining it to you. I think the general point they're trying to get at is when you introduce interaction terms like x1 squared y1, x1 squared x2, sorry, this is in the data. So x1 squared x2 plus x1 x3, and these will have their own coefficients beta 1 2, beta 1 3. So as soon as this starts getting introduced, now this derivative no longer remains this simple, plus whatever it has, whatever interaction terms, and it's not that easy to interpret. So there are different ways of still trying to interpret it in terms of the change in x versus y. But this statement, the flat statement, is obviously false, that with interaction terms, it is no longer the case that increasing x1 by 1 unit increases the response by beta 1. So what about the pictures that you can draw? Like maybe it's easier to plot how y changes with beta with x1 keeping all else constant. So sure, you can draw a plot, but that will also like be a um, single input variables at a time, or if there are more than. So for a single input variable, maybe you're still able to draw a plot of how. Sorry, this is a two-dimensional plot. So you can take y1, you can take x1, you can maybe still plot somehow how y changes with x. Y, not y1, my bad, this is y. You guys are understanding what I'm saying, right? Because I'm struggling a little bit to explain, but I don't want that to sort of make you confused. So the point I'm trying to get at is in linear regression, there is a straightforward parameter interpretation. When you add interaction terms, that gets more complicated, and suddenly it's not that straightforward. Earlier, what we said was y, x1, there is some slope beta 1 that tells you how much y changes with every unit change in x1. Here, that beta 1 is no longer that obvious, like it's not a slope of a line, this is some curve, because this also varies with, there is some beta 1 3 and beta 1 2 term involved because of these interaction terms. So that's the point. The fact that smoothers don't give us a simple story about how each input is associated with the response may seem like a disadvantage compared to using linear regression straightforward. But whether it is or whether it is not is really dependent on how big a lie you are prepared to tell in order to keep your story simple. Like I can still say, oh, roughly, x changes this much with beta 1, which is not strictly speaking true because there are these beta 1 2 and beta 1 3 terms, but people make up stories with regressions, and or or people literally ignore these terms, assume that it is a linear regression, and then work with that. So that's we'll get more into regression analysis in terms of the parameters when we do causal inference and what it means. Anyway, that was the interpretation. This is again the same. This is the mathematical version of the same thing that we wrote. Oh, I could have just shown you this. Damn it. Yeah, this is literally the exact same thing. And the second point, the same thing holds true if you ignore interactions but now consider that there are nonlinearities. So the true regression function might be of this form, and now interpreting the parameter, the changes in y with respect to x becomes very difficult. So we cannot sensibly talk about the response to a 1 unit increase in x. Um, Yeah, I mean it just gets at alternatives to, okay, how do we actually interpret these coefficients, and what can we say if we can't directly say that y changes with respect to beta with respect to x as beta 1. mm, and it gets at this particular formulation, which is called the average predictive comparison, because with the goal of, we want to boil this y versus x change down to a single number for each input variable. Then how do we go about this? And this gets us the average predictive comparison. Here you're talking about u and v, same sort of setup. I and j run over data points, mu hat is our estimated regression, and the sign whatever. So that basically ends the chapter. So what is this interpretation, and how do you boil your change in response with respect to change for every input to a single number using this average predictive comparison? Questions?
Suppose they said in kernel regression, like we kind of get the same value of it irrespective of data here. So, but in that also, like it's based on like some functions or mappings, like basically what rules we define, like. So that is also based on some like internally connected to data only, in some point,
No, no,
because we
I
will be making
corrected
rules
myself.
based on data.
I corrected myself
Sorry.
immediately after. So if that's the point you're getting at, then you're definitely right. I didn't mean it is independent of the data.
Okay.
Yeah, thank you. Thank you for clarifying. Mm, yeah, this was like very, very rough. I also didn't prepare this. It was pretty last minute, so I'm very sorry if I'm saying something really wrong that I haven't thought about much. Um, one like a couple of things you should think about after this is parametric versus non-parametric regressions. What we spoke about, choice of kernel, um, this convergence part. I definitely want you to work through it and understand why he's saying what he's saying. What does convergence of error mean? What is being talked about here? I want you to understand this terminology. At least, if not remember it, at least know where to look for the answer when you come across such terminology. Just like that level of familiarity is fine with me. You don't have to know what it means, you have to know where to go to find what it means. This was a very important section that we very easily breezed over, but one of the questions, I think 4.1, was based on this, and there is a discussion on the channel about it, and I thought I added a solution to it. Yeah, there was a link to the solution to read more about what 4.1 is, because we had a lot of discussion about this boxcar kernel, and showing this sort of value, what little o means. So big O notation is of the order of, so by similarity, by analog, little o notation is at the most this is of the order of, so is less than or equal to this order. Or actually, the specific term I looked up was ultimately less than the order of. So slight nuance, just less than, not equal to. Anyway, this is important. Please try to solve this yourself. If you have questions, please post on the group. We have discussed this before, so I think we'll be happy to point you to that discussion. Yeah, that's about it for this chapter. We can, um, I I mean, questions are, it's open to questions anytime. I'm just scrolling up to 3. Okay, so this is a simulation, linear smoother optimism, difference between the in sample while with the model from new data taken at exactly the same XI values. Okay. Have you all had a chance to actually go through chapter 3 questions?
I have not gone through the questions yet. I've just read the chapter. Right?
Yeah, me too.
No, the reason I'm asking is because these guys have done like we can walk you through them, but like should we walk you through them, or do you want a chance to actually go through them yourself and then discuss it?
Yeah, I would say like let us first try, then like we can have a discussion on that.
That sounds fair. So we can do one thing. We can have a session next week, which is an open session. There's no agenda for it. You can raise your doubts. You can raise your conceptual doubts. Whatever said and done. The week after that, we'll actually go through questions for chapters 3, 4, 5 together. Um, or we can postpone that based on what time you've had and how much you've done, or change the number of chapters we're doing. And we can pace ourselves after that. Just for the next couple of weeks, let's get you all on the same page, solve some questions, because this is hard stuff. It is not trivial. It is not easy to think about, and it is completely new notation. I can imagine it is a lot to take up in the middle of other things. So I don't want to like push, and I also don't want to just sort of jog ahead with the rest. So that, I mean, this ultimate decision is up to Fanny Kushal Parth, because they're the ones who already done all of this. So
Yeah, we don't mind. So, but maybe if they can finish reading everything by next week, then maybe we could, with the open session, we could do some of the questions as well next weekend. Depends if they're able to finish it off. Yeah, whatever works for them, because we are now the next step for me and Fanny would be starting with chapter 7. For the
Mhm.
three of us, including you.
Mhm.
So whenever these guys are done with completely finished with chapter 6, then we can go to chapter 7 after that.
Yes, if you can have like, I agree. If you all want to have a session next Saturday, but if we can complete the exercises and then go over the question, then go over the doubts. Like, if that makes sense. We tried doing